the thing that we like to highlight from this study is that this kind of extreme ozone formation events happen very early in the fire season. So there are definitely a lot more we need to understand. There's a certain level of urgency with it. So NOAA has been dedicated to improving our capability in understanding weather, including fire weather and its impact on air quality. So the current NOAA air quality forecast capability includes not only high resolution, rapid refreshing smoke forecast at 3-kilometer resolution, but also slightly coarser resolution configuration, but with fairly detailed smoke chemical characteristics. So the animation on the left-hand side shows the agency's flagship smoke forecast model, or the HER smoke model, which has been very widely used by not only scientists but also stakeholders too. And okay, here comes the however part. However, despite decades of research, it's still very, very challenging to represent wildfires in our modeling systems. And one major reason is that the model grids are too coarse for most of the wildfires. So the animation on the left-hand side shows a close-up view of the modeled plume of a fire plume with an active fire size of 1 square kilometer. The one important thing to know is that the wildfires, they can leave remarkable burn scars as seen from space, but the active burning areas are mostly very small. So what is also shown here is what the 3-kilometer grid box looks like. And obviously the plume dynamics cannot be explicitly resolved by a 3-kilometer model. And most of the fires in reality, they have active fire sizes smaller than 1 square kilometer. And HER smoke model is operated at 3-kilometer. Therefore, although the HER smoke model is generally considered as a fairly high resolution model, the resolution is insufficient to resolve the wildfire plume dynamics in the early stage. Now, in the eyes of modelers, a wildfire is nothing but a small point source emitting a bunch of heat and chemicals. And then the buoyant smoke plume would rise in the model and then do other things like interacting with model chemistry and physics. So the first challenge for us modelers is, where do we place this point source? Well, horizontally is relatively straightforward. We can just look at the satellite detection and use that to determine the horizontal extent of the fire source. But vertically is a lot more challenging and tricky as well, and that's what we're going to focus on today. So the plume rise refers to basically the process during which the buoyant plume is lifted in the model, reaching a certain level of stability. And this level or altitude is usually referred to as plume injection height. So plume rise has been identified as a major source of uncertainty in wildfire modeling. And imagine that if the plume is injected into the wrong altitude, then the smoke transport can be very off. So here I'm demonstrating a case with very strong vertical wind shear. That means the wind blows towards different direction at different altitude, and with the same smoke being injected at different altitudes. As you can see that the smoke transport and impact on downwind air quality can be very different. So here I have two real-world examples here demonstrating how plume injection can affect smoke transport. The top row is the sheep fire that we sampled a few years back during the FireSAQ field campaign, which was jointly funded by NASA and NOAA. And this fire was heavily affected by very strong near-surface wind, and the plume injection is overestimated by the model. And we can see that essentially in the model, the plume is transported too further away. And the bottom row shows another very interesting example, which is the Williams Flats fire. So this case was very interesting because the smoke triggered the formation of pyrocumulus. This is a very interesting and special type of fire clouds. So the model failed to capture this effect, and the model injection height is underestimated, and hence the plume is transported to the wrong direction, essentially. It's kind of like depositing money into the wrong bank account, which is kind of awkward, and the rest of efforts essentially doesn't matter that much. Now, if we come back to the physics, we can take a closer look at what exactly affects the plume rise. So plume rise is affected by several processes. For instance, the most important one is the heat released from the fire, which is a major driver of the plume rise. In the meantime, the turbulence around the fires can create small swirls, which can suck the cooler background air into the plume. And this process is usually called entrainment, and this can have major impact on plume dynamics. And last but not least, with the right conditions, some fire smoke can trigger condensation or produce the so-called fire clouds, pyrocumulus or pyrocumulonimbus. And when the condensation happens, it can release the latent heat, which can further drive the plume rise. So the moisture processes can definitely play a role. Now, so how should we model the plume rise? So ideally, we need the turbulence scale modeling tools, such as the large eddy simulation model or the LES model. So these models they can explicitly resolve the plume dynamics and hence plume rise. But these kind of models are very expensive to run, and therefore it's almost impossible to scale up in the foreseeable future. In reality, most of the times we're probably stuck with convective scale or mesoscale models, and the resolutions of these models are definitely too coarse to resolve the plume dynamics, at least in the early stage. So what can we do here? Well, you know the common wisdom, if we can afford it, we can definitely pretend it. The idea is that we can use the very expensive but fancy physics-based model to train the machine learning algorithm, and then pretending we're running this fancy model in the coarser resolution models. This is definitely one popular way to use machine learning approaches in Earth system modeling. All right, so when it comes to machine learning, you've probably heard that the training data set is very important, and the training data set has to be comprehensive. So because of the LES models are very expensive and the inputs can be pretty complicated, so the inputs of the LES model needs to be simplified so it can be run many, many times. So here we have identified 12 variables representing wide ranges of stability, wind, and moisture, and heat flux conditions. And then the Latin hypercubed sampling approach is used to construct a comprehensive data set with 6,000 samples, and each is used to drive one set of LES simulation. So this data set is used to train the machine learning algorithm. And because the inputs are systematically varied, this training data set is quite comprehensive. So in order to further test the machine learning model, another more realistic testing data set is also generated using the LES model, in which case the LES model here is driven by randomly sampled Hertz sounding profiles. So this test data set is driven by the realistic Hertz sounding profiles. Therefore, it's a more rigorous way to evaluate the model, but it's a lot less comprehensive than the big training data set because you can see the sample size is a lot smaller. All right, here I'm demonstrating what does the LES generated training data set look like. So the top two rows show the two demos in the comprehensive training data set in which the inputs are systematically varied to capture as wild ambient conditions as possible. So this is a key here because the training data set has to be comprehensive because in layman's terms, the machine learning models are not very good at extrapolating. So the bottom two rows show two demos in the realistic testing data set. As you can see, the LES model is driven by realistic Hertz sounding profiles. Therefore, it provides a more rigorous way to test the machine learning models. All right, in this project, three very widely used machine learning models are tested: a random forest, a gradient boosting, and a neural network. So the machine learning model takes 12 input variables, or in the machine learning world, people call them features. So the features kind of describe the heat flux, stability, moisture, winds, and stuff like that. And then the machine learning models spit out the three outputs: the plume top height, plume center height, and plume bottom height. Okay, so this slide summarizes some high-level performance of the model. And here I'm showing results from the three machine learning models from left to right. I have the random forest, gradient boosting, and neural network. And the rightmost column shows the benchmark model, the very widely used the Freitas scheme. And the top row kind of shows the evaluation using the comprehensive training data set. And we can see that all three machine learning models outperform the Freitas model. And the second row, which is pretty exciting, that it shows the evaluation using the realistic testing data set. And we can see that the machine learning models also shows promising performance. And that is what's even more exciting is that the machine learning models trained using the fake data performs well on the realistic data it has never seen. And the bottom three rows kind of show the statistical distributions of the plume top, plume center, and plume bottom. And we can see that machine learning models capture the plume profile shapes reasonably well. The Freitas model, on the other hand, it does capture the plume top height pretty well, but it definitely it tends to overestimate the plume center and the plume bottom. All right, you might be wondering what's going on with the very widely used Freitas model. So the Freitas model, the behavior of the Freitas model has been well documented in the past. So here I'm showing three representative examples using the LES models here. So the first model, the first example is affected by the very strong surface wind shear, and the Freitas model struggles with the polarization of the near surface wind shear induced entrainment. And the second example shows a case that triggered condensation, and the Freitas model, which is equipped with a very simple microphysics scheme, failed to capture this effect. And the third example is interesting because in this case, the Freitas model got the condensation roughly right, but failed to balance that with the effect of the very strong wind. Okay, here I'm showing some detailed diagnostics demonstrating that the machine learning models here are robust and not overtrained. So overtraining essentially refers to a regression model that performs, exceptionally well on training data set, but poorly on new data set it has never seen. So put it nicely, an overtrained model is largely useless. So here I'm demonstrating that the neural network model shows persistent performance across a new data set it has never seen and with low biases, small variances. And so these are all important targets we're trying to hit. So this indicates that the neural network model is probably not overtrained. It performs the best among these three models. The gradient boosting model, on the other hand, shows a minor sign of being undertrained actually. So another very commonly asked question is, okay, I have 100 samples, I have 1,000 samples, or I have 10,000 samples. Is that enough to train a machine learning model? So it is pretty difficult to directly answer that question, but we do have tools or ways to tell if the training sample size is sufficient. For instance, here we can gradually increase the number of samples made available for training and monitor the performance of the model on the training and validating data set. And the results here show that the sample size is probably sufficient for the neural network, but the gradient boosting model is definitely a little bit data hungry, which is also a minor sign of being undertrained. All right, so machine learning sometimes is criticized for being a black box. You dump something in, you got something out, and you have no idea, nobody knows what's going on inside the box. So here I'm demonstrating two important things. So firstly, the models are transparent, and most importantly, the results are physically sound, consistent with our physics-based understanding. So the first plot shows that the so-called permutation feature importance, which is a universal approach that works for that you can use to evaluate all type of machine learning models. So we can see that despite the models being trained and configured very differently, so all three models they show very similar results. For example, all the models are consistently pointing out that okay, heat flux is one of the most important input, which makes perfect sense because sensible heat flux is a dominant source of fire-induced buoyancy. And also, all three models consistently show that the near surface wind, especially the wind shear, also play a quite important role, which is also consistent with recent studies. And this type of feature importance is quite useful and can tell us the relative importance ranking of all the inputs. But it doesn't really tell us anything quantitatively. So the bottom plots, so we're trying to show essentially shows the partial dependency analysis. It really reveals the highly nonlinear nature of the problem. For example, we can see the plume injection height is sensitive to the heat flux, but to a certain extent until it hits some sort of plateau. After that, other factors start to play a more important role. And also, the partial dependency analysis also reveals the surface wind and wind shear have a negative impact on the plume injection height, but even also more so on the lower end. Okay, so this machine learning based plume rise emulator definitely shows promising potentials. What I didn't mention is that it also has improved the computational efficiency as well. So the next step, we definitely would like to implement that to the regional and global models, but that's actually quite complicated. And there are some unique challenges we have to deal with. For example, all the models are as good as their inputs. And sensible heat flux is extremely challenging to get from satellite observations. And Laura has done a lot of fantastic work on this subject, and she can tell you how challenging it is to estimate heat flux for wildfires. So the sensible heat flux is a common issue that faced essentially by all the plume rise models. So what can we do about it? And I know that communities are actively trying to improve that. But one approach us modelers can do is to use data simulation approaches to trying to assimilate satellite-based aerosol layer height products. So I'm going to take the rest of my time and briefly talk about the satellites and how we can utilize them to improve the wildfire smoke modeling together with the machine learning-based plume rise emulator. So before doing that, I'm going to very briefly review our current observing capabilities. So there are several satellite-based aerosol layer height products out there, and based on very different physical principles. For example, the operational ALH, or aerosol layer height product from the Chuopomi, and also AOCH, and AOCH stands for aerosol optical centroid heights, which is an algorithm recently developed by Professor Jun Wang's group at the University of Iowa. So recently, the same algorithm is applied to Temple as well. So our group is leading the evaluation of the Temple AOCH product. And also there is this stereoscopic ghost algorithm developed by Dr. Mario Freeberg and colleagues in NASA and the University of Maryland. And we are primarily using these three sets of satellite-based observations. All satellites are indirect measurements and needs to be thoroughly understood and evaluated before using them. So we have been using LiDARs and radars to evaluate the satellite-based aerosol layer height products. And actually, LiDARs are kind of considered as gold standards when it comes to wildfire or aerosol profiles or structures. But the deployments of airborne light and ground-based LiDARs are logistically pretty challenging and also expensive. And spaceborne LiDARs are great, but they suffer from very narrow swath paths. So recently, more studies to start use weather radars to study wildfire plume in structure and dynamics. The radars are, not exactly designed to detect smoke aerosols, but the wavelengths can capture larger pyrometeors, such as flying ashes, burned pine needles, and things like that. So the NextRad network has about 106 radar stations across the United States. And based on our experience, the chance that if you happen to have a radar station, within let's say 50 miles or something like that from a wildfire, there's a decent chance that the fire may be captured by the radar. So here is one interesting example showing the mosquito fire that we sampled a few years ago during the NOAA Cal Fire Field campaign. But here I'm only showing the radar and satellite results. So the smoke from this fire triggered the formation of pyrocumulonimbus, injecting the smoke all the way up to, I think, 12 kilometers. And we can see that the NextRad radar captured the smoke development pretty well. And the top row shows the results from the retrieval from the stereoscopic retrieval, which captured the smoke top features and also the formation of fire clouds too. And very interestingly, for these kind of fire clouds, because they are legit clouds, and the stereoscopic retrieval shows pretty good agreement with operational ABI cloud top product. The bottom panel, I'm showing two results from two other satellites, from MISR and Chuopomi AOCH. So MISR flies on the polar orbiting satellites, therefore it's overpassed with a late morning overpass time, which is not ideal for wildfire research because most wildfires are more active in the afternoon. And also the Chuopomi AOCH algorithm is affected by very thick smoke or fire clouds, therefore sometimes would struggle if you're interested in regions very close to the fire sources. And here's another example. I'm showing the Temple AOD and AOCH in the middle, and we can see that the Temple being the geostationary satellites, its hourly scanning capability is remarkable. But in the early morning and very late afternoon, the algorithm is affected by very thick smoke. Although the stereoscopic algorithm is not affected by this, it is worth noting that the stereoscopic algorithm is looking at different part of the plume. For example, it's actually looking at the smoke top features, while for example, the AOCH is sensitive to the smoke center. Therefore, we do expect some discrepancy between these algorithms. But this also gives us ideas. For example, the smoke center retrieved from the AOCH can tell us where the smoke is the thickest, while the stereoscopic approach can show remarkable capability to detect very thick smoke or even fire clouds, which the AOCH is struggling with. So far, we're trying to develop a data simulation system that can simultaneously simulate multiple satellite-based aerosol and smoke layer high products. And with that, I'm going to wrap up, and I'll be happy to take any questions or comments. Thank you very much.
Thank you so much, Siyuan. I really enjoyed hearing about your research. As we wait for questions to come in, I can start with a question of my own. I have to admit, I have never heard of a machine learning model being overtrained before. Can you talk a little bit more about that and how that happens in the first place?
Yeah, so the training data set, it's important. It can contain a lot of very useful information. On the other hand, the training data set can also contain lots of noise. So if you're trying a little bit too hard to tune the model to capture all the fine the noises are not something that we're trying to capture. Then the model may be trying too hard to capture those fine details and making something out of nothing. So if you're applying for this kind of models in real applications, and it's probably going to produce hallucinating results. So that's my kind of explanation for overtrain. It's kind of like, okay, you have a bunch of data points, you're trying to fit that with a straight line, but you have some noises, and you come up with very crazy curves to fit all those, to capture all those details. And if you're trying to apply that on new data data set, it's essentially dictated by the straight line, and there you're capturing all those noises, you're going to make something up. So that's kind of like rough idea of overtraining.
That makes sense. Thank you. We have someone who they say, I don't have a question. I just want to compliment the overall quality of your presentation material and how excellent your Python plots are.
Thank you so much.
And we do have a question. How can machine learning be used to predict ignition sources and fire behavior in different ecosystems? Do you have any insight there?
Great question. That's beyond the scope of this work. So what my vision for our project is that we take the satellite snapshot of fire detection, that kind of stuff, and we take the meteorological forecast and we dump that into the machine learning model, and the machine learning model can predict the plume injection height based on the meteorology and also the satellite-based fire detection. So that's the extent of it. I know there are some efforts they're trying to use machine learning approach trained by either observations or using fire behavior models to trying to emulate or mimic the fire spread. And that's, our approach, our project focus on the vertical stand. That kind of efforts looks at the horizontal stand. I think combining them together would be a great framework for our future wildfire research. But that's a little beyond of what we're trying to do at this moment.
Okay, awesome. If anyone else has a question, feel free to put it in the question box. We have another minute or so allotted for this Q&A portion. And I don't see any questions coming in at the moment, but please feel free to enter your questions throughout the webinar, and I can send them back to the speakers. We did get one other question. What is the status of incorporating this type of model into regional scale modeling?
We're working on that, and currently, so there are a couple of things we have to overcome. For example, to load the Python stuff into the models, which are mostly written in Fortran. There are some interfaces that are available, and there are also some Python-based like overhead calculation that we have to figure out what's the best way to deal. For example, do we have to rewrite all those things in Python in Fortran, or can we have some sort of like Python wrapper, or those technical details? And there are a couple of other things we're trying to figure out. Firstly, like I mentioned before, is the difficulty or the challenges in estimating sensible heat flux, which is one of the most important input of this algorithm of this plume rise model, and all other algorithms too. And we're also trying to come up with a workflow that can incorporate more information into the system. For example, by considering the moisture and latent heat flux from fuel moisture content, so that hopefully we can improve our model capability of improving of capturing moisture process, especially pyrocumulus. So a couple of items on our to-do list.
Great. Another question, what was your process for feature engineering when approaching this problem? You mentioned a physics-based neural network approach. How might you approach that?
I'm not sure if I understand the question completely, but basically, I'm kind of a physical scientist, and I understand what is going on under the hood. So when it comes to determining, okay, what features are probably important, we come from physics. We know that A, B, C, and D, these are important processes. So we try to build the model around these known physics. But we're trying to go a little bit beyond that, because our physics-based understanding is probably not perfect, and we have to also consider the what is plausible in the physics-based model, which is a large eddy simulation model, which has some constraints and limitations. So I'm not sure if I answer your question properly, but if not, please feel free to shoot me a message, and I'll be more than happy to chat more.
Yeah, please do. And we have one final question for this Q&A portion. Can LES effectively capture buoyancy-driven dynamics and plume behavior in extreme wildfire conditions?
Great question. That comes back to how you configure and set up the LES model. And in theory, I think it definitely can. But in my application, because this is the first stage of the application, I did not know how long it would take for me to generate all this required training data set. It actually took me more than 2 years to generate all the training data set using large eddy simulation model. So I did not intend to capture the extreme events that can inject stuff directly into the stratosphere, because I don't even have a stratosphere in my model. But in reality, we have been discussing how to deal with this kind of stuff. So if the plume injection model kind of determines, okay, the smoke can reach all the way to tropopause, we can maybe come up with some simple energy balance approach in the stratosphere, trying to mimic that process to a certain extent. But that's definitely one limitation of my LES model. And LES model in general, it has some considerations and limitations, but it should be able to handle extreme events. It's just in my application, I'm not fully exploring that option, because this is just the first step.
Got it. Well, thank you so much, Siyuan, and thank you for everybody who entered in questions. We're going to move on to our next presenter now, Laura Thapa. So Laura is a postdoc in the Barnes Group at Colorado State University and a recent PhD graduate from UCLA. She's working in the prediction of climate change influenced natural disasters, including wildfires and coastal flooding. So during Laura's time at UCLA, she contributed to a project supported by the Climate Program Office's AC4 program, or the Atmospheric Chemistry, Carbon Cycle, and Climate Program. And this project was focused on improving emissions, predictions, and impact assessments of biomass burning, smoke, and dynamic air quality. So Laura has now transitioned to her postdoc position at Colorado State, and she's focusing on other phenomena like sea levels now, and still using AI tools to advance her science. So we're excited to hear about your work, Laura, and go ahead.
All right, just want to make sure that everyone can hear me.
Yes, we can hear you.
Okay, awesome. All right, hi everyone. I'm super excited to present today. I'm Laura Thapa. I'm a postdoc at CSU, and today I'm going to be talking about my PhD work, which I did at UCLA with Pablo Saide as my advisor. And my talk today is on forecasting daily fire radiative energy using data-driven methods and machine learning techniques. So before I get into some science, I actually want to talk about how my year started. So I am actually a remote postdoc at Colorado State, and I actually still live in West LA. So the picture on the left is showing the view out of my PhD office window in around January, beginning of January of this year. And UCLA was actually located right next to the Palisades fire, which was a really large and destructive wildfire that occurred in January. And across town at the same time, there was another fire burning in Altadena called the Eaton Fire. And because these were two traditional kind of Santa Ana wind driven events, that means that the smoke from these two fires was kind of blowing out across Los Angeles and over the ocean. And it turns out that these two fires had a total economic impact of around $250 billion. So living through this event, kind of while I was during my postdoc and finishing up my PhD, really reminded me about like why we should care about this research. And the Palisades and Eaton fires really fit into this trend of increasing wildfire activity that's driven by climate change. So in the left plot here, I'm showing wildfire burn area in the bar chart, and then vapor pressure deficit anomalies in the solid black line. Vapor pressure deficit being, of course, a measurement of atmospheric dryness and water demand. So what we're seeing in this plot is that as the Western US is warming and drying, we are seeing an increasing amount of fire activity. And this 2021 paper that actually came out of a group at UCLA determined that around 2/3 of that VPD increasing trend that's shown on the left is actually attributable to anthropogenic warming. And the fact that we had large wildfires in January of 2025 kind of bears that out for at least LA. These large wildfires are also putting up large amounts of smoke that is degrading air quality across the country, as Siwan mentioned in the intro to his talk. This is a figure from Burke et al., and it's 2023, and it's showing annual average PM 2.5 across the continental United States. Since around 2000, when the graph starts, PM 2.5 was on the decrease, in a large part due to regulations like the Clean Air Act. However, in around 2016, this trend starts to stagnate, and in 30 of the 48 CONUS states that were used in this average, there was smoke influence on the increasing or reversal of the previous decreasing trends. So how does my work fit into this field? So my PhD focused on the way we represent wildfires in our air quality forecast. And the way this process works is it starts with an estimation of wildfire activity. So there are many satellites that are monitoring the Earth at any given moment. And from these satellites, we are able to determine the sort of intensity and location of wildfires around the globe. And from there, we are able to compute how much smoke is being emitted. These smoke emissions are then fed into a chemical transport model. These models will compute the dispersion of smoke in space and time, and they will tell us the sort of physical and chemical changes the smoke will undergo as it is transported through the atmosphere. Finally, experts can read the output of these chemical transport models to produce an air quality forecast. And members of the public can look at these forecasts and see, are they in danger of unhealthy air quality due to smoke? And then other stakeholders can use these products as well. So in my PhD, I focused on improvements to our wildfire activity estimations and predictions, as well as to our chemical transport models. And I tested to see if these improvements led to better air quality forecasts. But in particular today, I'm going to talk about how we can use ML tools to better estimate and predict wildfire activity for fires that are already burning in our models. So I want to talk a little bit about how we're actually computing emissions in our air quality models. So these wildfires that we observe are putting out a ton of heat, but it turns out that only around 10% of that heat, and this fraction is still pretty debated, but around 10% of that heat is radiated out to space and is then observable via satellite. The remaining 90% of that heat goes into like convective processes or conduction, heating the fuel and evaporating moisture, etc. So of the 10%, the satellites are going to be measuring a quantity called fire radiative power, or FRP, which is essentially the amount of energy that the fire is releasing per unit time. So it has units of megawatts or energy per second. In order to compute emissions, what we do as scientists is we sum up or integrate that fire radiative power over time to get a total energy, or the fire radiative energy. And then to go from fire radiative energy to emissions, we use a very fancy scientific technique called multiplication, where we make the assumption that the emissions are equal to the fire radiative energy times a constant, where the constant will depend on things like the fuel type and the species we are looking to compute the emissions for. And what's really neat about the fact that emissions are directly proportional to fire radiative energy is that it really simplifies our problem. So if we're interested in predicting these little wiggles or how fire emissions are going to evolve over time, it's really simple, because all we have to do is then predict how fire radiative energy is going to change over time. So in my project, I set it up so that my ML algorithms and other methods will predict this delta FRE, or this daily derivative, where it's the ratio of FRE sub T, which is fire radiative energy tomorrow, divided by fire radiative energy sub T minus 1, which is fire radiative energy at time, like today, for instance. So we're going to be trying to predict this delta FRE quantity. So actually what the current operational models do is they assume that this delta FRE is equal to 1. And that's called persistence. And it's the assumption that fire behavior tomorrow or throughout your forecast period is going to be the same as current fire behavior. So on the left, we have an example of a persistence forecast in white, and then the corresponding observations of each day in orange. So in the first few days of this fire, we see that persistence does a good job. It's capturing days it's capturing the behavior of the fire when the fire is not changing. However, the big pitfall of using persistence is that if we have these days of extreme fire growth, like the 8th, or days when the fire dies off, like August 9th, persistence is by definition going to miss that. So our idea was to use ML and other data-driven methods to give us better predictions of delta FRE. Now, throughout this talk, I'm going to be evaluating our model that makes these predictions in 2 ways. I'm going to be evaluating our model's predictions of delta FRE, and to do that, we're going to look at whether or not the model is able to predict increases and decreases in fire behavior. And then I'm going to show some evaluation of the model of the model's predictions of FRE actual values. And in order to get these FRE values, all we have to do is rearrange the equation. We get a predicted FRE that's a persistence term times the predicted delta. And I can step this forward into as many time steps as I want. And I will be evaluating both 1 and 2 day predictions of fire radiative energy here. Since this is a machine learning problem, I think this kind of came up in C1's Q&A session, we're going to be using our domain knowledge of the drivers of wildfire in order to, as the inputs to our ML algorithms. So we're going to be training our models on a set of variables. We are going to give our ML model some persistence information. So we're going to give it previous measurements of fire radiative energy, and these are going to come from the RAVE dataset, which is a blended geostationary and polar orbiting product that computes FRE and emissions on an hourly basis. Then we are going to give our model information about what experts call the fire behavior triangle. So this is weather, topography, and fuels. And then finally, we are going to give our model some information about current firefighting efforts for the different fires that we're going to be predicting. So let's get into it and look at some examples of model performance. So the first plot on the left that I'm showing is for the persistence model. And since we're looking at the delta FRE quantity, we're going to be testing to see if our models are able to predict increases and decreases. And our best models are going to have all values, all colors right along this diagonal line, indicated by the black arrow. But because this is a persistence model, all our model is capable of doing is predicting those slight changes, and it cannot predict any increases and decreases. One more sophisticated approach we can take is we can assume that that our predicted delta FRE is equal to some sort of delta of fire weather. And in this case, we're using the hot, dry, windy index, which is correlated with fire rate of energy and is the product of the vapor pressure deficit and the wind speed. So when we use delta hot, dry, windy to predict delta FRE, we are able to predict some increases and some decreases, and we see that we are filling up this this sort of diagonal that represents higher accuracy. Finally, we tested a random forest model that was trained on information about fuel, weather, topography, and firefighting from 2019 and 2021 and tested on 2020. And by the way, this is all test data from 2020. So far, of these three models, our pure machine learning random forest model is our most accurate. We are able to predict many increases and many decreases and predict them very accurately. So as we go from simple persistence model to the scaled method to random forest, we are getting better FRE forecasts and increasing accuracy. So this is kind of mentioned in Suwon's talk as well, but in order to build trust in a machine learning algorithm, we kind of have to open up that black box. We need to understand what the machine learning algorithm is actually learning. And we also need to understand when and where we can trust our models. So let's kind of build some trust in our model right now. So what we're going to be doing from here on out is looking at when and where we can trust our random forest model. So here I'm showing error of the random forest model in the solid line and the persistence model in the dotted line as a function of fire behavior. To the left, we have these cooler or less intense fires, and to the right, we have the hotter or more intense fires. And because I'm looking at root mean squared error, that's the yellow, or mean absolute error, that's the teal. Our good models are going to have lower error, and our bad models are going to have higher error. So what we see right off the bat is that error increases as a function of fire intensity. So these larger wildfires are just going to be harder to predict, whether we're using machine learning or persistence. One really exciting thing I see here is that across the board, we're seeing the solid line lower than the bottom line, lower than the dotted line, excuse me. And what that tells us is that across all of these fire categories, the random forest model is more reliable than persistence. So this is still very much a bulk evaluation. So let's break things down further and figure out when and where and in what locations we can trust our random forest model. So in the table on the right here, I'm showing you the percentages of the days in the 2020 test set where the random forest model gives us a better prediction than persistence. And this is quantified using the skill score of root mean squared error. So for both our 1 day and our 2 day predictions, we predict our random forest model gives a better prediction than persistence over 60% of the time. And this is really important, specifically that we're higher than 50%, because if we were just random guessing, we would get 50%. If we restrict the days to days which have at least 10 active fires, that skill score increases, the percentage where we have a positive skill score increases even more to over 70%. So that was an evaluation of the time series. Let's look at how the random forest is doing spatially. So here is a plot of the R squared, or the explained variance, for a 2-day persistence forecast averaged over each state in our domain. What we see is that at 2 days, persistence becomes a pretty useless model. We're seeing lots of blue across the board, which means that this model isn't doing a great job. However, when we bring in a 2-day random forest model, we are seeing some pretty large improvements across certain states. For instance, we improved California and Washington by a lot. Those go from, and Arizona, they go from being negative to positive. However, there are still some states where the R squared values are negative, like Oregon and Montana, but those R squared values are still improved a lot. The next question then becomes, okay, why are some states having a better time? Like, why are some states easier for the random forest to predict than others? And it turns out that this is actually a function of fuel moisture, where states that tend to have drier fuels are easier for the random forest to predict. And this kind of makes sense intuitively, right? Like, there is a threshold at which too much fuel moisture is going to like cut off fire growth. So let's look at some different skill metrics. So here is a 2-day persistence forecast, and this is the root mean squared error as a function of states. We see that California, Oregon, and Wyoming have high RMSE, and that RMSE is decreased when we apply the random forest and make a 2-day prediction. And similar to previous work, this shows that states that have higher intensity fires are a little bit harder for the random forest to predict. So this is consistent with what I showed previously. Another metric we can look at is the F1 score. This is a metric used for understanding how well classification does, or how well a model does classification. And it looks like for predicting increases, our model does a really good job across the board, across all states. We're seeing a lot of reds, which means the model is better. And then similarly for predicting decreases, we're seeing that our model is doing a good job. And again, things like weather and fuel moisture will explain the patterns that we're seeing in these skills. So finally, we needed to interrogate our model and figure out what it was actually learning. So what I'm showing here is a plot of various skill metrics for different configurations of the model. And the top row and these vertical dotted lines represent our baseline model, which is the model trained on all available features. So that's going to be fuel, weather, topography, firefighting, and persistence. Excuse me. And our baseline model, let's focus on the blue dots here. So our baseline model explains around 48% of the variance in the observed 2020 FRE. And what we do then to test what our random forest model is actually learning is that we train versions of the model that are missing certain key predictors. For instance, we train a model that doesn't include a persistence term. And then we train a different model, which doesn't include any information about weather. And we see that when we drop persistence, our variance explained goes down to around, I think, 0.46 or 0.47. And when we drop weather as a predictor, our variance explained goes down to like 30%. So what this tells us is that our model is getting worse when we leave out information on surface weather and current fire intensity. Therefore, we can assume that the model is learning important information from these features, the model as trained. Well, hang on a minute. We didn't just train our model on persistence and weather. We also gave our model topography, fuel, and firefighting information. What about those predictors? Well, it actually turns out that when we dropped those predictors and retrained the model, the performance was kind of comparable to the model trained on everything. And so what that means is that for the model we have trained and for the science question that we have asked, maybe fuel, topography, and firefighting in their current form aren't the most useful features. So by construction, our project kind of built in a lot of redundancy in our features. We really wanted to look at all available predictors. It was particularly covering the fire behavior triangle. And a great way to look at that is to look at all of the weather variables we tested. For instance, we tested the fire weather indices from the Canadian Forest Service and the US Forest Service. We looked at the hot, dry, windy index, which can be computed from any model input. We looked at vapor pressure deficit, wind speed, and temperature. And then we looked at derived indices like the hourly wildfire potential, which comes out of NOAA. So, and those are just ways that we can represent the weather in our models. And this goes along with fuels and topography as well. So our next experiment was to sort of come up with synthetic subsets of the feature space that represent the kind of data that would be available to different agencies, such as the US Forest Service and the Canadian Forest Service. And when we looked at these synthetic data sets, these combinations of features, we saw that the performance was really was really stable across the board. So all that kind of tells us that all of these different agencies are equipped to do a good job in predicting these daily changes in FRE and thus the daily changes of emissions. All right, so why does all of this matter? So in this presentation, I showed that we are able to reliably predict the delta FRE with machine learning. We are able to come up with methods that are more accurate in predicting increases in fire behavior and decreases in fire behavior than persistence. And our fire radiative energy forecasts themselves are more accurate than those produced by the persistence model, under certain situations and subject to certain caveats. So then my question became, and this is actually some plots from the final chapter of my thesis and my final PhD paper. The question then became, do our better predictions of delta FRE actually translate into better smoke forecasts? So if we apply these predicted changes in emissions that are ML derived, if we apply those in a real life weather forecast, such as one from the WRF Chem model or the GEOS model, do we actually get better predictions? So for these two figures, what I'm actually plotting here is domain averaged aerosol optical depth, which is kind of like a total column measurement of smokiness. And I have observations in red, and then our three different model configurations that we tested. We tested a model with like observed emissions, a model with persistence emissions, and a model with random forest emissions. And after a lot of digging, the best I can tell you is that sometimes using machine learning derived smoke emissions estimates gives us better forecasts. But when we get into the model world, there's a lot of things that we have to think about. We have to think about like underlying model uncertainty. We see that our models are underestimating AOD. We have to think about things like plume rise. For instance, the WRF Chem model uses plume rise and the GEOS model does not. So, and it turns out that the little changes that we made with our delta FREs that we predicted using machine learning are really hard to find in an actual air quality forecast. So kind of that's where I'm at with my PhD work, but I wanted to wrap this talk up by talking about some of my postdoc work. I totally changed gears during my postdoc. I often tell my friends that I changed elements. I used to study fire, now I study water. And in my postdoc, I'm looking at using machine learning and explainable AI to predict subseasonal to seasonal sea level predictability, to examine this predictability. What I've done so far for this work is I've really honed in on looking at the west coast of North America, and I've kind of grouped some of these coastal points into clusters based on how sea level varies over time in these regions. And then I am working currently on training some neural networks to make predictions about sea level on S2S timescales in these clusters. It's been really awesome to kind of get my hands on the neural network and the PyTorch code and play around with that. And another awesome piece of my postdoc work is that I'm using I'm building ML models that instead of like a deterministic prediction like I did for my PhD, they're actually able to predict distributions and quantify some uncertainty. And with this work, I hope to explore questions related to like forecasts of opportunity and understanding physical processes or regions that are driving these forecasts of opportunity. So thank you all so much for listening, and I look forward to your questions.
Thank you, Laura. That was great. Reminder to everybody, the way we're going to do the Q&A portion is if you could please put your questions in the question feature. So I do have some questions coming in already. The first one is, what exactly is included when you say weather in the random forest model evaluation?
Yeah, it really depends on which. So within the world of fire weather, there have been many efforts to come up with like single number representations of the sort of weather impact on fires, and those are just like broadly called fire weather indices, and they really range in complexity. Like one of the simplest ones is vapor pressure deficit, which is kind of the atmospheric water demand, but also different it's I guess generally thought that like low humidity, so dryness, temperature, high temperature, windiness. Those are all kind of the like kind of raw variables that would go into some of these fire weather indices. But they just get computed, and like you can do like different fits to get a better sense of like to correlate these values with FRP.
Great, thanks. The next question is, how does data quality impact the accuracy of ML-based FRE predictions?
Oh, yeah, that's a good question. Um, I think a place that we really saw that was when we were looking at fuel data. So I didn't really get a chance to talk about it, but for fuel data, we looked at things like fuel type, fuel moisture, and fuel moisture is one of those things that's really hard to quantify. And there are many different data sets that try to quantify it, and they're all very different, and there's a lot of uncertainty. And so I'm wondering if, like, for instance, the uncertainty in fuel moisture related to that not being a super helpful feature.
Thank you. Another question, what initially attracted you to using random forest? Did you consider any other ensemble machine learning approaches to predict delta FRE or even deep learning?
Yeah, so I use the random forest. I think random forests like intuitively make a lot of sense because you can think of like the decision trees as like if this then this. And a lot of fire behavior stuff is very threshold based. Like if the fuel's too wet, it's not gonna burn. I did try support vector machines, I believe, and I think I tried a simple uh like a two hidden layer neural network kind of situation, but the random forest just kind of made intuitive sense. Oh, and also the random forest does have a built-in feature importance method, which is really cool.
Okay, great. Thanks. I think for the sake of time, we're going to have to cut it there, but I will, there are some other questions in the question feature, and I'm going to pass them along to Laura so we can get those to you and try to get your questions answered. But for now, I would just love to thank both of our presenters for being here today, and thanks for sharing your work. We really enjoyed hearing about it. The Climate Program Office and the NOAA Center for AI is really excited to host more webinars in this series. The one that we have scheduled right now will be on April 29th from noon to 1 Eastern Time, talking about some research using ML and AI in climate variability and extremes. So I also put some resources in the chat to learn more about the NOAA Climate Program Office and the NOAA Center for Artificial Intelligence, NCAI. You can also feel free to reach out to me directly with any questions about either of our offices or about the webinar series in general. So thank you so much, and we hope to see you next time.